Okay. So thank you for being here. I'm Diego Garcia, and I'm gonna talk about my work on my thesis called "Modeling of Advanced Electrodeless Plasma Thrusters," under the supervision of Mario Merino and Professor Eduardo Aya. Um, I'll go briefly through the contents of the presentation. First, I'll give a brief motivation about the electrodeless plasma thrusters and magnetic arc expansion, very briefly because you have heard already a little bit about this from my colleagues. Then I'll talk about the thesis objectives, what I've done in the past, what I'm doing now, the methodology, and the next steps for the following year. Well, first, the motivation. What are electrodeless plasma thrusters? Basically, electrodeless plasma thrusters, EPTs, as we call them, are a type of space propulsion, electric propulsion devices, which work by energizing electrons via electromagnetic waves, as Celiano was talking before, and accelerating the plasma in a magnetic nozzle. The advantages of this kind of thrusters compared to, for example, Hall effect thrusters, which other friends will talk about, basically stem from the fact that we don't have any plasma-weighted electrodes. And this makes, in principle, the possibility of having longer thruster lifetimes using alternative propellants and so on. Basically, what happens in an EPT, the main operational principle, is that we accelerate the plasma in a magnetic nozzle, which is just a convergent divergent magnetic field here, as the one you see here. And this confines and accelerates the plasma thanks to the Lorentz force. Basically, what we're doing is just converting the electron thermal energy into directed ion kinetic energy thanks to an ambipolar electric field that is formed in the nozzle. Usually, EPTs are run in configurations such as this one. This is a helicon plasma thruster. But we wanted to study what's the expansion of a plasma in noble magnetic geometry that we call the magnetic arc, which is just this kind of closed line geometry that Celiano already talked about. Which could appear in in different situations that could be interesting for electric propulsion, such as magnetic nozzles with opposed polarities or novel concepts such as the magnetic arc thruster, offering, in principle, a reduction of magnetic dipole that couples sometimes to the magnetic field of the Earth, producing torques, possibility of thrust vectoring, and, in principle, a lower plume divergence. So the objectives of my thesis were basically writing fluid code to simulate electrodeless plasma thrusters and use this code to understand the main physics of the expansion of plasma in a magnetic arc. This I talked a little bit about already. I gave some preliminary results already in the doctoral meetings of last year. But this year I was able to complete that work. And I've also started studying cylindrical magnetic nozzles, studying different effects with some modifications I've done to the code lately, which I will talk about later. Well, basically, the methodology I've used, last year I had already developed two-fluid code consisting of a quasi-neutral collisionless plasma formed of massless, polytropic, and perfectly magnetized electrons, and cold and singly charged ions. Basically, the code I wrote solves these equations using a discontinuous Galerkin, spatial discretization, and evolves them in time with Runge-Kutta time stepping. And lately, in these last months, I've done some extension of the code. Basically, I improve the solver for the self-induced magnetic field. I run simulations on the expansion self-consistently with the self-induced magnetic field of the plasma, which we thought for the magnetic arc that would play a big role. And I included in the last couple months some extensions to the code to account for collisions against a neutral background to simulate facility effects on ground testing, and also introducing neutrals in the equations. Well, for the first part, the results on the magnetic arc expansion, last year I talked about already on the first assessment of the expansion of plasma in a magnetic arc in the beta zero limit. What we did this in last summer and in the end of the last year was to study the effect of the self-induced magnetic field. What we have seen is basically that the self-induced magnetic field, we have here the total magnetic field for different beta values. Here for beta 0 up to beta 0.08 in equal distances, 0.02, 0.04, 0.08. And what we have seen is basically that the self-induced magnetic field, as we expected, opens the magnetic streamlines, as you see here. In fact, there's a separatrix line here depicted in red that appears for the higher beta limit. And what we have seen is that this effect of the opening of the lines increases the thrust, the total thrust of the produced by the magnetic arc. Here we have the results for the different betas. Well, as I was saying, I did some extensions to the code lately in the last couple months. By the way, forgot to say it. We just released we just published the article, which was accepted a couple weeks ago, about the expansion on the magnetic arc. And we did a recent extension to the code to account for collisionality with a background of neutrals, because we've seen in some literature review that it affects the total magnetic thrust of the nozzles, and it may affect the possibility of ground testing EPTs in vacuum chambers. And what we have seen indeed is that when we include the collisionality against a background of neutrals, we have a lower ion velocity. The ions are slowed down by the background of neutrals, but the ionization, the late ionization in the plume, produces more plasma that is subject to acceleration. And globally, what we have seen is that increasing collisionality increases the total thrust produced by the nozzle. So in the end, we presented this work at the conference, Plasma Tech, in April in Lisbon. And what we concluded is that basically we have to be very careful with ground testing EPTs because of this background pressure affecting the performances of the nozzle. Right now, at this moment, I'm working on some preliminary results because I included, as I said before, the code until now was a two-fluid code, but I introduced a third type of, a third fluid in the equations, including neutrals in the model, completely solving the neutrals in the model. In principle, we would like to study if we have neutral depletion in the nozzle with the late ionization to gauge the influence of neutral dynamics in the expansion of these magnetic nozzles. And these are some preliminary results because, as I said, I still have to fully test this part of the code for the collision frequencies, for the ionization percentage. This is at the center line. And for the total thrust of the nozzle. So for the next steps, things I have to do in the following year, I want to finish with a full validation of the three fluid equations to be completely sure that all the effects that we see are real. To assess the neutral dynamics, the effect of the neutral dynamics in the nozzle, to totally assess the effect of background pressure on the expansion of the magnetic nozzle, and if we can, we'll write a paper about it. We hope. And some other possible extensions we could do to the code is adding the ion energy conservation equation to the model, and then after that we'll start writing the thesis. So this work was done in the framework of the Zarathustra project, the ERC Zarathustra project. And if there's Any questions? Thanks a lot.